next speaker is Dr. Raja Sakamuri. He is currently a postdoc at the University of Louisville in the chemistry department. He previously was 4 years postdoc in the chemical engineering department at the University of Louisville. He received his PhD at the Indian Institute of Technology, Madras, India. He has spent 6 years with the Indian Petrochemicals Corporation Limited as a senior research official doing research in catalysis. While in the chemical engineering department at the University of Louisville, he's worked on hydrogenation processing. His interests are in general heterogeneous and homogeneous catalysis. Today, he's going to talk to us about synthetic and mechanistic studies in palladium catalyzed transfer hydrogenolysis of haloaromatics. Raja?
As different from other speakers, my talk is not related to vapor phase heterogeneous catalysis. So it is liquid phase heterogeneous catalysis, the one my talk is related to. As is seen from the title, the topic of our discussion today is centered around transfer hydrogenolysis. To introduce this topic, it is relevant to recall our understanding on the fairly related topic, that is hydrogenation or hydrogenolysis using molecular hydrogen, so that we can relate our understanding, compare and contrast between hydrogenation versus transfer hydrogenation, or hydrogenolysis versus transfer hydrogenolysis. For our work, we have used formic acid and its salts as hydrogen donors. The relative efficiency of these hydrogen donors towards a given reaction has been established, and those results will be presented. And kinetics of transfer hydrogenolysis of a chosen reaction has been done. And from this kinetic, the chosen reaction is nothing but hydro-dehalogenation of haloaromatics using sodium formate in the presence of palladium carbon. Now, using kinetic results and some spectroscopic, mostly mass spectroscopic results, and we have proposed a mechanism for hydrogenolysis of haloaromatics. Finally, I will conclude and then put forward some suggestions. Now, as you know, ethylene hydrogenation is a well-studied reaction and is one of the best textbook example. The thermodynamic is feasible, and delta H is negative. That means exothermic. For that matter, almost all hydrogenations are exothermic. And the entropy is decreasing because we are making one molecule out of two. And when temperature is around 500 K, the delta G is again negative. Therefore, the reaction can say it's highly feasible. But if you mix ethylene and hydrogen, nothing happens because there is a barrier. So the barrier could be the hydrogen molecule, which has a bond energy of 104 kilocalories, and this hydrogen is highly symmetrical and is non-polar. And also to reaction to form fissile reaction, the geometry should be favorable. In the case hydrogen-hydrogen, distance is 0.746 and carbon-carbon is 1.337. It shows the geometry is not favorable for a reaction. And also, to a fissile reaction to take place, the interacting orbital should have a suitable symmetry. In the sense, the interacting orbitals for hydrogen is the HOMO, that is highest occupied molecular orbital of hydrogen. And here, this is the lowest unoccupied molecular orbital of ethylene. So if you look at the symmetry, they are not compatible. Therefore, we can say that concentric addition is orbital symmetry forbidden. So these are the constraints for the reaction to take place. Now, to catalyze this reaction, and we need to, or to proceed this reaction, we need to activate both substrate as well as hydrogen. Now, as you know, the substrate activation is much easier rather than hydrogen. Therefore, we will concentrate on the activation of hydrogen. Now, this can be achieved either by acid-base catalysis or redox catalysis. Now, there are few examples in the literature that H plus and OH minus can catalyze hydrogenation. That means it can activate hydrogen. Now, if you look at the compound used for hydrogenation, it is a superacid. It's highly acidic. Either HF-PAF5 or HF antimony pentafluoride has been used for this purpose. And in the case of hydroxide, tertiary butoxide has been used to catalyze the hydrogenation, but the conditions are too severe. That is 200 degrees Celsius and around 100 atmospheres of hydrogen. Therefore, the reaction conditions are too severe to be practical. On the other hand, the transition metals or their complexes having suitable ligands can catalyze any hydrogenation reaction effortlessly, even at ambient conditions. Now, the proposed mechanism for this is, now the hydrogen can be activated on the transition metal because of the presence of d orbitals, and thereby you can say the dihydride. And now these can add on to the ethylene very easily. Now, the geometry constraint is removed here, and also the symmetry constraint again removed, because here the minus, minus, plus, and minus. Now, if you look at this, I have avoided the pi bonding orbitals. What I have shown here is it is only anti-bonding orbitals, that is a pi star. Now, this mechanism was proposed based on the fact that diimide can add on to the ethylene in a concentrated fashion, here without catalysis. This is just a stoichiometric reaction. So based on this mechanism has been proposed. But in fact, most of the hydrogenation reactions follow a stepwise addition. That is, hydrogen gets activated on transition metal, and this add on to the olefin to form an alkyl, and this further add on to the another hydrogen to form saturated compound, and the catalyst is regenerated. Now, therefore, so these are the transition metals are excellent for hydrogenation. Now, let us talk about the transfer hydrogenation. Now, the transfer hydrogenation is hydrogenless hydrogenation. Here we don't use hydrogen. So instead, we use what is known as hydrogen donor. Now, this is the reaction, representative reaction mentioned here. The similar equation can be put forward for hydrogenolysis. Now, the driving force for this reaction to take place is the oxidation potential of the donor should be smaller than the oxidation potential of the acceptor. That is one of the important criteria. Now, practically any functional group or unsaturated functional group can undergo transfer hydrogenation, similar to hydrogenation. Now, there are variety of hydrogen donors have been listed in the literature, but I have chosen only very few representative examples. Now, the secondary alcohols can donate hydrogen to form ketones. And in the cyclic compounds like cyclohexene, cyclohexadiene, and tetraline can donate hydrogen to the various unsaturated functional groups. The driving force for this class of compounds is the gain in aromatization energy, because they can donate hydrogen and then become aromatic compound. In the case benzene here and naphthalene there. And in the case of formic acid and ammonium formate and the hydrazine, the driving force is the liberation of a very stable compounds like carbon dioxide here, carbon dioxide, ammonia there, and here the nitrogen. So these are the driving force for this to donate hydrogen. And these last two are the two excellent examples as of inorganic hydrogen donors, whereas all of this organic hydrogen donors. Now, you know that various functional groups can undergo hydrogenation in the presence of a transition metal catalyst. Similarly, using a proper hydrogen donor, all these can be undergo transfer hydrogenation using a proper hydrogen donors. Now, similarly, hydrogenolysis, these are the very representative functional groups which can go hydrogenolysis. Especially this is hydrocracking, here hydrogenolysis of various functional groups. These are all hydroprocessing industry, these are interested. Now, we and the lab we are interested in these 4 functional groups. Now, if you compare this hydrocracking CC bond cleavage, hydrogenolysis can be, through hydrogenolysis this can be achieved, whereas through transfer hydrogenolysis it will be difficult because we need very severe conditions. So except this, we can pursue these functional groups using transfer hydrogenolysis. Now, what we are going to talk today will be on this CX hydrogenolysis, to some extent CO hydrogenolysis. Now, early in 1980, from our lab, we discovered that ammonium formate as an excellent hydrogen donor for hydrogenolysis purpose. So this is the protected tetrapeptide, and this is the product. Now, using a palladium and carbon, we have achieved the reaction in few minutes. Now, the purpose of the reaction is so fast, and you can achieve at neutral conditions and ambient temperature at 20 degrees Celsius. So this reaction is so famous because we can avoid hydrogen, and we have abbreviated as ammonium formate catalytic transfer hydrogenation, the AFCTH. And this is being routinely used in our lab and around the country and elsewhere because of its simplicity. Now you see that the separation of the products is also very easy. Just filter it out, we can separate palladium and carbon, and here the hydrogen goes there, and the carbon dioxide is liberated, it escapes, and the ammonia also escapes. So this is an excellent example of transfer hydrogenation at ambient conditions. Now the same method has been extended to remove chlorines from polychlorobiphenyls. These are all pollutants, in fact. So you can remove these chlorines and get biphenyls. Now this reaction, using these reagents, you can achieve in 4 minutes a complete reaction. Now we have also extended the same method using a butylated compound and butylated solvent and palladium carbon to incorporate heavy atoms like deuterium in a biomolecule like peptide here. Now, as you are aware, now to track down a biomolecule like peptide or a drug, generally we incorporate heavy atoms like deuterium or O18 or radioactive elements like tritium or C14 to track down to trace the injected drug. But at that time, though I have mentioned here as a D, only one monobutylated, but actually we got a dibutylated compound also. At that time we didn't know the exact mechanism of dehydrohalogenation here, therefore we couldn't explain satisfactorily why the dibutylated compound is formed. Now, coming to the transfer hydrogenolysis or transfer hydrogenation in general, not much mechanistic studies have been done. Most of the studies are only synthetic in nature. So we decided to probe into this, and then to start with, we have selected transfer hydrodechlorination reaction. That is, we have selected 4-chlorotoluene as our substrate, and the formate salts, I'll talk in detail here. And palladium carbon is an excellent catalyst, so that's the reason why we stick to palladium carbon. These are products of toluene, carbon dioxide, and corresponding chlorides. Now, these are the reaction conditions for our study. 2 or 4-chlorotoluene, both function very well. Hydrogen donors, say formic acid, lithium formate, sodium, potassium, cesium, ammonium, and triethyl ammonium. And catalyst is 200 milligrams. And solvent, we have used a mixed solvent system because of the solubility problems. And temperature is 20 degrees Celsius. Now, we have shown from our lab that ammonium formate is better than formic acid. And somebody else from Israel, that is Hassan and Blum of Israel, have shown that sodium formate is better than formic acid for a given reaction. But a systematic study is non-existent in the literature. So to start with, we decided to find out the relative efficiency of various formates because they are all excellent hydrogen donors. So a comparative study is essential. So to meet that demand, so we have chosen various formates, that's formic acid, lithium, sodium, potassium, and cesium also we have selected. And these are the various results. Formic acid here for hydrodechlorination reaction. This is the lithium, and this is sodium, this is potassium. And the cesium results we also got, but we didn't plot it because it's very close to potassium. For clarity's sake, we have avoided cesium results. And ammonium is there, and this is the triethyl ammonium. Now from this, we can get a very qualitative picture. That means if you compare the group A formates, that is hydrogen, lithium, sodium, potassium, cesium, there is a trend, that is formic acid here, lithium, sodium, potassium. That means if you go down the periodic table, the rate increases. Or in other words, the best way to compare the results is initial rate. They are the meaningful comparison can be made. But what we thought was, we want to go a little bit deeper and then trying to correlate with any property of this group 1A element to get a quantitative picture. So that is what our aim. So we have these are the three meaningful properties to compare with the initial rates: ionic size, electronegativity, and base strength of hydroxides. We have included the base strength of hydroxides because they are the precursors for all the various formates. Because what we have done is formic acid and sodium hydroxide, and so all the hydroxide we mixed and then to get the salt. But if, as you know, all the alkali metal hydroxides, they are all categorized as strong acids, and they dissociate 100% in water. Therefore, there is no much to compare with the base strength of hydroxides with the initial rates. So then the ionic size and then electronegativity of the element as well as the cation. Now we try to correlate with these electronegativity results with various initial rates, but we didn't get any proper correlation. We do get the correlation, but they are not really linear. Then we are settled down with the cation size. This unbelievable correlation was obtained up to potassium, and beyond potassium, some other aspect is contributing. We believe that maybe diffusion, we are reaching the diffusion range, and at the same time, we have not established that the diffusion is the factor there. If you look at this, it's already we are 65 millimoles per liter per minute. So that is one of the consolation that we are in the diffusion limited rate. Now this is the explanation for. So these are the alkali metals, the general formula. These are the oxygen of this formate versus the ionic size. As you increase the ionic size of the metal, we are increasing the distance and thereby reducing the electrostatic interaction between the O- and M+. And thereby the formate ion is available for the chemisorption on the palladium, thereby increase the activity. So that is the explanation we have settled down. Now coming to the other two ions, which are very commonly used, like triethyl ammonium and ammonium. So we have grouped together with the H+ again, because we have the pKa values for these all the three compounds. Now based on the pKa values, this is the trend we expect. That is triethyl ammonium followed by ammonium, but H+. But what we observed is ammonium is better than triethyl ammonium, better than H+. So this is the property we have selected. Now the explanation given here is the triethyl ammonium is too big an ion, so the steric factor may be contributing to this because it prevents the formate ion to adsorb. Now the model might be very, very useful to convince you. So this is the ammonium ion, this is the triethyl ammonium ion. So probably because of the steric hindrance, the formate activity is lowered there. Now let us focus on the formic acid, because it's a very interesting one because it doesn't show any activity at all. Now why is formic acid less effective? But it has been shown in the literature that formic acid can be used as a fairly good hydrogen donor for some other reactions. Now then these questions we thought that concentration of formate ion could be a limitation, because we thought formate ion is important for the reaction. Now if you look at the equilibrium here, the Ka is very, very small. Now suppose if you shift the equilibrium to the right by trapping this H+, then again we are producing more formate ions. Now this is our idea. Now in this, if you look at this, this is the formic acid results. When we add ammonium acetate, we have chosen the ammonium acetate as a base because of the solubility reasons. If we add ammonium acetate after 30 minutes, now the rate jumps and the reaction is completed in 210 minutes. Now the same base, if I add in the beginning itself, again the reaction can be completed in 90 minutes. Now, if you calculate the initial rate here and the initial rate there is a difference. This is 25 millimoles per liter per minute, whereas this is 37 millimoles per liter per minute. So the difference in initial rate we attribute to the deactivation of the catalyst by the HCl formed in this region, because hydrochloric acid is the one of the reactants that produce formic acid. Now this is the chemistry of the base addition. That is, when formic acid is reacting, when ammonium acetate is added, we get ammonium formate and acetic acid. Now this is, we believe that these two are formed based on these values. That is, Ka of formic acid is this, and Ka of formic acid is 1.75 × 10⁻⁵. Therefore, in our system, these two compounds are present. Now, if you look at the reaction here, it is no way different from the ammonium acetate earlier we have used. It is what we are generating is ammonium acetate. Naturally, the ammonium acetate is excellent hydrogen donor. Except that, only difference is the acetic acid is the one we are producing there. Therefore, we have not got much information out of this. Now, what we got only information what we got is the deactivation of HCl in this region. Then we will go back and see that what is the before that. If the equilibrium or the concentration of formate is the limitation, then what we should have observed is there should be a slight, say there is an increase up to 2%, and there should be a slight gradual increase of conversion with time. That's however little it may be, but we didn't get that. So there is a complete poisoning of the catalyst, or our reaction is arrested after 2%. So thinking in those lines, we thought the other possibilities. Inhibition of the product is another possibility. So what are the products we look at here? The 2-chlorotoluene, formic acid, toluene, carbon dioxide, and HCl. HCl being a strong acid can be dissociated into 100% H plus and Cl minus. So toluene is not a poison. We know it is being used as solvent. Carbon dioxide is a poison because actually carbon dioxide liberates from the solution and then escapes. And Cl minus also is not a poison for this catalyst. So therefore, H plus is a culprit. Now the culprit is a general word. So what we know is HCl can deactivate the catalyst to some extent, but it is not poisoning the catalyst completely. Therefore, we have designed two experiments. One is you replace the formic acid with an active system like sodium formate, which is very highly active as hydrogen donor, and add hydrochloric acid to this system, and then see that whether the HCl is added HCl will generally deactivate the catalyst. Now the another system what we have chosen was you use some other reagent to reduce this, which can generate HCl, so that we can see the effect of HCl on this. Now these are the two systems. Now the sodium formate reserves are here, and when you add hydrochloric acid, and now this is the, as long as there is no poisoning of the catalyst, what we got is this graph. Now what is happening here is the hydrochloric acid combines with the sodium formate and forms formic acid and sodium chloride. Therefore, this experiment is not suitable to explain hydrochloric acid inhibition. The second system is the traditional hydrogenolysis using molecular hydrogen. This is the hydrogen used, and this is HCl is formed here. Now look at the graph. The hydrochloric acid formed is not poisoning the catalyst. What it does is there is a gradual conversion increase with time, but it takes 40 hours to complete. But when you add an ammonium acetate, which is a base, to this particular system to trap hydrochloric acid, now you see that reaction is completed in 55 minutes. So from this we can gauge that hydrochloric acid deactivates the catalyst, so it does not poison the catalyst. Now how do we explain the results then? Now we'll go back and then see reaction. Now in this case, what we observed is when the 2% conversion, enough hydrochloric acid is formed, and this hydrochloric acid, as being a strong acid, suppresses this equilibrium. Therefore, very little, that is, or almost negligible amount of formate ion is present in this particular system. So that is indirectly HCl is arresting the reaction, and it is not poisoning the palladium carbon catalyst. So that is a conclusion. Now at this stage, what we know is hydrochloric acid deactivate the catalyst. And formate ion is very important species for transfer hydrogenolysis. Now, we have chosen a representative of a reaction to follow a detailed kinetics. This is the reaction order determination. Now, if you look at the reaction here, rate constant A, B, and C, where the A, B, C are substrate, hydrogen donor, and the catalyst. Now, to arrive at the mechanism, what we need is the reaction order, that is superscripts A, B, and C, and those can be obtained by these three plots. To get obtain the results for these three plots, these are the experiments designed. When you are changing the 2-chlorotoluene, and these two are maintained constant, and when you are changing the sodium formate, and these are the ones which are constant similar with the catalyst. The following three slides will tell you, will give you the exact data. Now, when you plot initial rate of 2-chlorotoluene with initial rate, what we got is a straight line. That means there is no change in initial rate with respect to initial concentration. That shows the order with respect to 2-chlorotoluene is 0. Now, second, when you plot initial concentration versus initial rate, that is of sodium formate, at the lower conversions, on the lower concentrations, it is a linear, and beyond that, there is a deviation from the linearity. That means something else is happening at the higher concentration. That will come in a moment. Now, with respect to the catalyst, it is perfectly linear. This order with respect to the catalyst is 1. Now, in addition to the kinetic data, we also can get some idea from the product analysis. So, suppose if it is sodium formate, that is hydrogen form, what we get is toluene, 100% toluene. When you replace sodium formate with the deuterated sodium formate, what we expect is 100% this. If all this deuterium replaces Cl minus, what you should get is 100% D. But instead, what we got is this distribution. So now if you look at the stoichiometry of the reaction, this D, what we have taken, is just sufficient to replace all the chlorine to get this. Whereas if you look at this, there are D here, a D there, and a D3 there. Now the actual distribution can be seen here. So this is the D0, where there is no deuterium, this monodeutenated di, tri, and tetra. This is the clean statistical distribution of all the toluenes observed. Now if you replace, that means the benzylic CH3 or hydrogens are highly labile on palladium surface. So they get exchanged with the solvent. Now if you replace a benzylic, if you use a compound where there is no benzylic hydrogens, what we got is 88% monodeutenated and 12% non-deuterated. By changing the reaction parameters, that is by increasing the temperature, these are all 20 degrees, increasing the temperature to 60 and reducing the reaction time, maximum what we got is 92%, not beyond that. So what's happening here is some sort of exchange is taking place. That means the sodium formate is not 100%. Similarly, the solvent, deuterated solvent, they are not 100%, they are all 99 plus. And also the hydrogen might be coming from the catalyst, the carbon. Carbon has a lot of hydroxyl groups and carboxyl groups because they are all activated carbon. So they are contributing to this 12% conversion. Now, in addition to kinetic data, or before proposing a mechanism based on all the data what we have seen, what we thought was what we know about the formate ion, because that is supposed to be the and also what we know about the catalyst and how they interact. So this will tell us. Now from the X-ray and the electron diffraction, people have shown that these two bond angles are not same, whereas in the case of sodium formate, these two bond angles are bond lengths are same, 1.27 there, 1.27. Therefore, it is a resonance hybrid of the two forms. And the bond angle is 129 degrees. And from that bond angle, we have calculated the distance between this oxygen and that oxygen. It comes out 2.3 angstrom units. And also, this is the representative of this formate ion. That is, if you look at this, carbon-oxygen p orbitals overlap in both directions. Now, this I mentioned because these are the bonding orbitals which are responsible for the chemisorption of formate on palladium surface. Now, what we know about the catalyst? Now, catalyst is a commercial catalyst obtained from Aldrich Chemical Company. It is a 10% palladium on carbon carbon surface area is around 800 meters per gram. Now the XRD shows that the low index planes are present. The crystallite size is fairly, definitely it is more than 40 angstrom units, but we didn't calculate the crystallite size. We can calculate from the line Gaussian analysis. And if you look at this is a reference palladium, it nicely matches. And this is the impurity what we got. This is the graphite impurity present in carbon. So this is the graphite reference. So from this, we know something about the palladium, something about the formate, how they interact. Now there are 6 possibilities, or even more than that. The formate can chemisorb in a monodentate fashion or a bidentate fashion, or it can absorb horizontally or vertically. And for each formate, there may be one metal site can be involved or 2 metal sites. So there are so many varieties of possibilities are there. So Miles et al., who have determined the heat of chemisorption of formate on nickel-1,1 single crystal in a gas phase. They found that the heat of absorption for monodentate, that is eta 1, mu2 means 2 metal sites, is 59 kilocalories. That is smaller than when it is a bidentate, that is eta 2, mu2. And later, number of researchers who are working in the surface science, they shown that the formate ion chemisorbs on these all metals except copper in the bidentate fashion. When in the copper, both modes are possible. Now these results are summarized by Alex Bell of Berkeley in a recent book edited by Sustorovich. Now based on this information, these are the model has been proposed on the interaction of formate ion on palladium surface. First we will see the 1,1,1 plane. Now these 2 oxygens which are equivalent occupy the 2 hollow sides, and whereas carbon and hydrogen will sit on the top side. Now as hydrogen is interacting with the metal, that is palladium, the carbon-hydrogen distance increases, and this becomes a linear structure, and carbon dioxide is liberated, and palladium-hydrogen hydride is formed. The carbon dioxide leaves the surface and then escapes to the gas phase. Now these are all the sizes are all real. That means the palladium distance 2.75. This distance is 2.3 angstrom units. Now similarly, we can propose for 100 plane, and we can also propose for 110 plane. I have not shown here. We believe, if our model is correct, what we believe is 100 and 110 planes are much better planes for catalysis than 1110 planes for this sort of reactions. Now, finally, based on all this information, these are the mechanism proposed. First, we have considered this. You know that though sodium formate is a strong electrolyte, we have included this particular step to account for, we have seen that the deviation from the linearity when we plot sodium formate concentration versus initial rate. So that's the reason why we have included this. The second step is the formate chemisorbs on the palladium surface to form and absorb species, which is controlled by the equilibrium constant K2. And then the slow step, the palladium formate decomposes to palladium hydride and carbon dioxide. And in the fast step, the substrate chemisorbs on the palladium surface and form a complex, and then the reaction. The actual reaction takes place in the fast way. There is a palladium catalyst is generated, and which the cycle continues, and the product, toluene and chloride, is formed. Now the rate expression derived for this is the 2 rate expressions. One is for low concentration of sodium formate, and the another is for high concentrations. If you look at this, first order with respect to palladium, first order with respect to sodium formate, this explains nicely. And at a higher concentration of sodium formate, there is a fractional order with respect to sodium formate, whereas palladium, there is a order with respect to palladium is 1. Now, we have proposed this as a slow step. There is a possibility that these results or these rate expressions can be explained by assigning a slow step, this particular step. If you look at this, palladium is first order and formate is also first order. Now how do you differentiate between which one is slow step? Now to achieve this, primary kinetic isotopic effect came to our rescue. This is the sodium formate, this is the conversion level. When you replace with the sodium, deuterated sodium formate, this is the conversions we got. Now from the initial rate, we have calculated Kh by Kd, which is 1.87. Now from this, it is clearly shown that our mechanism proposed explains most of the observations and is close to reality. Now I will conclude that the hydrogen generating ability of group 1A formate salts is proportional to the ionic radii. The formate ion is an extremely vital species in transfer hydrogenolysis. Mineral acids like hydrochloric acid deactivate the palladium catalyst and doesn't poison the catalyst. The rate limiting step for dehalogenation is the dissociative chemisorption of formate ion. For that, we recently found that even for CO hydrogenolysis, the rate determining step is this. And the rate expression for hydrodechlorination is at low concentration, of course. And benzylic hydrogens are labile on the palladium surface and hence exchange with the solvent. Now, some of these conclusions are fundamentally significant when you explain, or if you want to explain the decomposition of formic acid on metal surfaces. Now, this reaction has been used in 60s and 70s by all the stalwarts to characterize the metal salts. Now, this has a very good fundamental significance to explain those results. I have not seen this sort of conclusions from their studies. These are the scopes and suggestions. AFCTH, ammonium formate catalytic transfer hydrogenation. Ammonium formate because it is one of the excellent hydrogen donor out of all the hydrogen donors I have listed. No doubt potassium is better, but ammonium has some other advantages. Related excellent potential in organic synthesis is a mild, rapid and simple method, and working up is excellent. The wide use of this system in industrial applications may be anticipated. In fact, we came to know that some of the pharmaceutical industries are using this particular method for large-scale synthesis, that means at least in kilogram scale synthesis. CTH represents a convenient method of preparing labeled compounds like deuterated and tritiated compounds, the radioactive compounds. In fact, we are pursuing this area now. Formic acid in salts are a very good source of hydrogen in asymmetric induction, because asymmetric synthesis is one of the excellent areas in pharmaceutical industry. Now, when you compare the hydrogen versus hydrogen donors, this has excellent advantages because the selectivity can be increased using the hydrogen donors. Finally, formate salts are potentially useful as chemical carriers in hydrogen storage and transportation. That is, this is hydrogen storage and hydrogen energy case. That means recently somebody from Israel have found that these are much better when compared to metal hydrides and absorption of hydrogen on the zeolites, etc. So this has excellent potential. And finally, the funds from NSF, Kerry Scott, and the NIH are greatly acknowledged. And help from Julie is greatly appreciated in preparing the slides. Thank you very much.
We have a couple of minutes for questions.
What kind of substrates can you hydrogenate with that?
Any substrate.
Olefins?
Yes, olefins.
Not aromatics.
Aromatics is a bit difficult, but there are instances aromatics can be done.
Phenols?
Phenols, yes. Nitro compounds. Nitro compounds, if you look at this, we have done nitro in 1 minute whole reaction under same reaction conditions. Nitrobenzene can be reduced to aniline in less than 1 minute. I couldn't do any kinetics at all. We need a fast.
What about benzoic acid? Carboxylate?
Oh no. We have to resort to lithium aluminum hydrate type of thing. They are all very inert.
Have you looked at CO2 is a product of rate determining step?
Yeah.
Looked at a CO2 atmosphere over the system to see if it retards that rate or has any effect?
These are all open systems, because what we do is in an open vessel and then carbon dioxide escapes. If you close it, carbon dioxide solubility might increase on the solvent and that might affect,
Quick question. You talked about the different cations affecting the rate of hydrogenation. They also use alkali cations to promote palladium catalysts. Have you looked at whether or not these ions are interacting with the surface and affecting the reaction?
There is another possibility. What we explained is based on the ion size. That is what the process what we got. Yes, there will be an electronic interaction between, that is the cation can alter the electron density of the metal here, the palladium 0, and thereby it can also alter. That is one possibility. But I still have reservations because it's in a solution because the interaction between the cation on the surface may not be as strong when we incorporate these cations on the catalyst and then do the catalysis. This possibility is there, but I don't know how far that will influence. I don't know.
Thank you very much for quite a complete discussion of the mechanisms. At this time, we have a 15-minute break.